Okay, so hello everyone, welcome to the IVM meeting this week. First, we're very sorry that we made a chaos because of the summertime change in US. So I'm pretty sure we should have much more audience than what we have now, but most likely we may need to give another talk in an hour again. But anyways, so let's first make a start. Today, we are very happy to have Dr. Venkata SubbaRao Redrouthu from Konstanz to talk about post-DNP. Rao got a bachelor degree in maths, physics and chemistry in 2005, and he then gained some experience on organic chemistry during master and started working on solid-state NMR during his PhD. And since 2018, he joined Dr. Jennifer Mass's group in University of Konstanz and started working on post-DNP. Today, he will be sharing experience on developing pulse sequences for DNP experiments at Q-band. Rao, the mic is yours. Feel free to start.
Yeah, good afternoon, everyone. Thanks for a nice introduction and also for the invitation. And today I'm going to talk about my experiences with pulse DNP at 1.2 Tesla. That's Q-band. Yeah. So somehow, sorry, I cannot see the screen. Sorry, there is a problem. Okay. Yeah, I cannot see the titles, but anyway, I will continue. So anyway,
we can see the title.
Actually, there is a bar which came and yeah, it's overlapped on top of it. So it is not going. Anyway, I will continue. It's not a problem. Yeah, DNP is all about improving the sensitivity of mass NMR by transferring the polarization from electron to proton. And to do DNP, we usually dope the NMR sample with unpaired electron, and then we irradiate the electrons using microwave. And then we see the electron polarization transfer from electron to proton, and we finally observe the enhanced NMR signals. And this method is well established, and we have commercially available mass DNP setup from Bruker and other companies. So by doing DNP, you typically gain the enhancement factors around 658. That is the ratio of their gyromagnetic ratios. But with the current with the CW method, to gain the enhancement factor, that the theoretical maximum is not possible. Yeah, it's not possible with the current CW method. The aim is to go to pulse DNP method, where we can do the coherent transfer of polarization from electron to proton by using microwave pulses instead of CW irradiation. By doing this, we can use the spin dynamics analogous to the transition from CW to pulsed EPR and NMR methods, and to improve the enhancement factors. By considering polarization transfer method is an optimal control problem, not likely that CW is the most efficient one. And also, it may enable us low duty cycle DNP, which reduce the sample heating. So this is the pulse DNP. What we do is, as I mentioned before, we dope the NMR sample with the free radical. In our experiment setup, we usually do with the title, which has a very narrow line shape, and it forms a very good glassy mixture at 8200 kelvins, and we do the pulse DNP. So when we do the when we apply the pulse DNP, and it transfers the polarization to neighboring protons, and then because of this spin diffusion from proton to proton, so it goes to the bulk, and then once the electrons are relaxed back, so we apply the follow-up pulse to do the same, transfer to the neighboring protons, and it spin diffuses to the bulk. So we repeat this process until all the protons are dynamically polarized. Then we can detect enhanced sensitivity, and we can see the dynamically polarized NMR signals. And the first pulse DNP sequence is novel, stands for nuclear orientation via electron spin locking, where we apply flip pulse followed by the flip pulse followed by the spin lock pulse for the contact time around 500 nanoseconds. By using novel, we typically gain enhancement factors around 200. But the problem with the novel pulse sequence is the matching condition. That is, like a CP in an NMR, we have to match the Larmor frequency of proton to the nutation frequency of electron to do the polarization transfer. The problem is when we go to the higher magnetic field, we need high nutation frequency. As we know, nutation frequency is inversely proportional to the microwave powers. So we need very huge microwave powers to generate that high nutation frequencies. The immediate alternative one can think of using off-resonance novel. So by incorporating off-resonance offset in the matching condition, one can do the novel. But the problem is when we go to the high fields, this offset is much greater than the nutation frequency. So and at the high fields, so the enhancements we see, which is inversely proportional to the offset, so we lose the efficiency at high fields. Kong and his co-workers come up with a new idea of incorporating modulation frequency in a matching condition by means of modulated pulse sequence. That is here, it's a top DNP sequence where it stands for time optimized pulse DNP, where we apply pulse followed by the delay, and we repeat this block to the contact time. So here you can see this 2D simulation where I have optimized the microwave resonance offset versus the nutation frequency. You can clearly see at a different matching condition where the Larmor frequency matches with combination of modulation frequency and effective frequency at these points. You clearly see the enhancements. Here is the positive enhancement. Here, this side is the negative enhancement. I will explain why we are getting positive and negative when I'm explaining the theoretical section. So this is the experimental field profile we did at Q band. And here also you can see this is corresponding to the 18 megahertz nutation frequency in this slice. So this is the experimental field profile we got. And recently we come up with the two new DNP sequences. They named after analogous decoupling sequences in NMR. They are XIX DNP and TPPM sequences, TPPM DNP. So XIX stands for X inverse X. That means we apply X followed by the inverse X pulse. And TPPM stands for two pulse phase modulation. So we apply pulse with the pulse and then usually pulse and then other pulse with the opposite phase. Usually we can write phi by 2 minus phi by 2 or like 0 and phi. So two pulse with different phases. This is the typical pulse DNP's pulse scheme, where we have the preparation pulse to get rid of all the initial polarization on nuclear spins. Once we have the zero magnetization nuclear spins, when we start the polarization transfer from electron to proton by means of pulse DNP, and then we can detect the nuclear polarization typically using the echo formation. And to get the optimized conditions, we wanted to do the numerical simulations. We selected Spinach to do the numerical simulations. So we do using the single shot as shown here, we just transfer just to the electron to the neighboring proton. And we selected one electron, two proton spin system, that is the 3-spin system, to do the numerical simulations. And they are separated around 3.5 angstrom that correspond to 1.8 megahertz dipolar coupling. We use the powder averaging and G anisotropy of 12 megahertz correspond to Q band to mimic the line shape. And we typically start with the magnetization along Z magnetization along x-axis, z-axis, Z magnetization of electron, and we detect the Z longitudinal magnetization of proton. And this is again the 2D profile where I optimize offset versus the nutation frequency for XIX sequence. Here also you can see the different matching conditions and corresponding enhancement in along these stripes. And this is the experimental field profile at Q band corresponding to 6.4 millimolar concentration. And for more results, you can look at this publication where we have more experimental results. And we did the full parameter space optimization of TPPM sequence, which is more generalized version of XIX DNP. Here I listed different pulse lengths corresponding and their phases where I find the very good conditions. So this is 12 nanosecond, 14 nanosecond with the 80 and 40 nanosecond with 100 and 60 nanosecond, 80 nanosecond, 22, and this is 28 nanosecond, that is 180 phase means XIX sequence, and this is 40 nanosecond and 50 nanoseconds. We wanted to do the experimental experiments for all these conditions. So this is the experimental setup in our lab. This is the Q-band setup. And most of the experiments I have done with Sanjay Vinod Kumar. And this is the Q-band experimental setup. And we upgraded this by adding the NMR console and RF amplifier. And here Sanjay tuning the Android Pro, which have the remote tuning box with the network analyzer. This is the first TPPM experiment where we optimize the phase of the TPPM sequence corresponding to 60 nanosecond, and numerical simulation we got 120, but in experiment we got at around 115. This is the field profile corresponding to TPPM sequence, pulse length of 60 nanoseconds. And we also optimize the contact length for the different pulse sequences like top DNP, XIX, and TPPM. And we compared with the numerical simulations, including the relaxations. And here is a comparison between the top DNP and XIX DNP, and top DNP with a high nutation frequency and the TPPM with the numerical simulation. If you see here clearly, the TPPM sequence with the 33 megahertz nutation frequency shows 3 to 4 times better enhancement compared to the other pulse DNP sequences in a numerical simulation. But when it comes to the experiment, it's hardly shows that difference. It's around 2 times higher. Maybe because the spin system we have chosen to do the numerical simulations, not maybe a realistic one. And this is the build-up curve optimization of top DNP, the top two are the top DNP and the XX DNP at different offsets and TPPM sequence. Here also you can clearly see that TPPM sequence is very fast in bulk buildup. Bulk buildup means like what we do is we apply the pulse sequence to the contact time, and then we repeat this pulse sequence for some number of times so that we see the bulk nuclear polarization. That means through spin diffusion, all the protons are polarized to do the NMR. This is the final results of pulse DNP for top DNP and XX DNP and TPPM DNP. TPPM shows close to 50% higher enhancements compared to the other pulse DNP sequences. These are the enhancement factors calculated corresponding, and these are the on-off signals I have tabulated, and these are the contact time which I used to do the pulse pulse DNP sequences. And here I listed the scaling factors and the analytical factors which I calculated from the theoretical analysis. So here, if you see the scaling factor for TPPM, which here it gives much higher compared to the top DNP and XIX sequence. So I'm going to discuss now how we calculate them and what is the relation with the final enhancements. So before going to calculate it, so I will illustrate how we do that. So as we all know that the time evolution of quantum system is described by the quantum level equation as given here. The simple solution of this quantum level equation is given with this expression. So where u is the time ordering with the exponent of integral of this time dependent Hamiltonian. When h is time independent, so it gives very simple solution. So this integration gives only it simplifies and you get this simple solution. So where this is we consider it as a propagator. So where we propagate the initial density operator to time t and then what we do, we calculate the observable corresponding at that time t. So in NMR we typically calculate the transverse magnetization, that is I plus or I minus. So how we do that? So as I mentioned, so when it is time independent, the time evolution is given by this expression. This is rho at t is given by rho naught evolved under H effective. So when H effective contains only the operator like X and Y and Z, so it just follow the simple rotation, like a sandwich rotation, like rotating around the coordinate axis. So we can simply apply this formula to figure out what is rho at time t. But when it comes to the when the Hamiltonian has the form like this, the combination of product operators. So to solve this density operator, it's not looking that easy to solve. So that's why what we do is we rewrite these sort of terms in a like a subspace that is double quantum subspace and zero quantum subspace. So where we have these product operators are listed here. So we can say that this operator entirely acts as a Z operator. This combination of X and Y gives X operator, and when we have the like this, it's a Y operator. Same for the zero quantum subspace. So what is the advantage of writing in a product operator in the fictitious operator basis? So for example, to solve the expression like this, we can rewrite this expression using here it is, we have Ix, Sx Ix and Sy. So this is what we have. So we can replace this one with the Ix14. So we're just doing that. And we can replace with the Iz with the combination of Iz14 and Iz24, like here. So, but Iz14, as I mentioned, so like it has a different subspace, so it will commute. So Iz14 do nothing to the 2, 3, so it remains like this. Then here you have Iz14, and so when X acts on Z operator, we simply can apply this sandwich rotation and to find the final expression. So it looks very simple to solve. Yeah, here I have listed how we do that. So as I mentioned before, so in NMR we want I plus and I minus, but in DNP we prefer to longitudinal magnetization, because that's what creates the bulk nuclear polarization through spin diffusion. The time evolution is given by this expression, as I mentioned before. So once we have rho naught along SZ axis, for electron it's minus SZ axis. So we can split this one into zero quantum subspace and double quantum subspace sort of thing. So this is the Z operator for double quantum and Z operator for zero quantum. And when Hamiltonian contains double quantum X or Y, so it evolves as a Ix cos theta plus Iy sin theta sort of thing, or Ix sin theta sort of thing. So we are only interested what we are getting from S spin to I spin. So we are interested only how much I is there. So this is what we have. So then when we have only purely double quantum, so we have this term plus the cos theta evolution is 0. So we get final Iz magnetization as this form. And when we have purely zero quantum, we have Iz magnetization as this expression. And I can show how we these things in a pictorial representation. So here, as I mentioned, we start with the minus Z magnetization, and we can rewrite that to the zero quantum and double quantum sort of thing. So this is double quantum Z magnetization, and this is the zero quantum. And when we have the Hamiltonian contains double quantum and zero quantum, it oscillates as a cos form. So here both the S and I oscillates with the cos function, and same with the S and I has the oscillate with the cos function, because we have the minus sign here. Oscillation is opposite. So when we add these two things, so this is the final result we get, where the Z magnetization for I spin is 0, but for S spin is oscillating from -1 to 1. So the trick is, so we target for I spin creation, but we are getting zero magnetization when we have the zero quantum and double quantum. But when we have only purely oscillation through zero quantum, so this is the double quantum, it stays where we started, and this is the zero quantum. So when we add these two together, this is what we get. We get the negative enhancement for the I spins. And same thing for the double quantum case. So when we have the Hamiltonian contains the double quantum, and there is no zero quantum terms in Hamiltonian. So zero quantum remains same, and double quantum oscillate with the cos function. So when we add these two for the final results, so that the I magnetization gives positive enhancement. And here, if you see here, the I magnetization is going from 0 to 1, and then it's coming back to 0. But in a real spin system, you don't see that, because we have the many powder orientations. So it's a powder sample. We have all the orientation possible. So we have a combination of all different dipolar couplings. So when we add the average of all these contact curves together, the average comes and oscillates around 0.5. And then we can now see the real application, that is for off resonance novel or solid effect case. So this is the Hamiltonian we have for the off resonance or solid effect case. So this is the Zeeman term, and followed by the hyperfine coupling term. This is pseudo circular term, and then this is the term corresponding to the microwave pulse. When we transfer this to the electron nutation frequency, so and then we drop this term, which is pseudo circular term, in the rotating frame, and now the time dependence in the microwave goes. Now what we do is we go to effective axis we go to the tilted rotating frame. What is the advantage of is that the effective rotation happens along the quantization axis. That's what we needed. So first we tilt the frame so that the effective rotation, because of the pulse, is happening along the quantization axis. So for that we need to this is the effective rotation axis, so we need to tilt to the theta so that it is along z axis. Once it is along z axis, we and then we can rewrite this Hamiltonian. So after tilting it, this is it. So I can rewrite into zero quantum and double quantum x and y, and also I can write it in the z operator, the combination of zero double quantum and zero quantum z operator. So now what I will do, I will transfer it to the interaction frame to find the effective Hamiltonian. So this is what I'm doing. I'm transferring using the interaction frame transformation given this unitary transformation to obtain the effective Hamiltonian. So this is the Hamiltonian form looks in the interaction frame. It looks like a time dependent, but when we match this matching condition, that is effective plus omega I is equal to 0, or omega effective minus omega 0 I is 0, that is zero quantum and double quantum matching conditions we typically see in DNP. We get time independent term corresponding to that matching condition. So this is double quantum matching condition. We get in the Hamiltonian, finally we get the double quantum X operator. And when we match the this term to equal to 0, we get the H effective as a double quantum X operator. So now we have the H effective in the interaction frame, and then goal is to calculate the density operator in the interaction frame. So that's what we are doing here. So this is the density operator in the interaction frame. We can rewrite this in tilted rotating frame. We always prefer do the calculation in tilted rotating frame. So this is the expression in tilted rotating frame. So for solid effect, now I can make two cases. One is a solid effect case and another is a novel case. In solid effect case, we have no flip pulse. So the initial magnetization starts at minus z direction. So once we have the apply the tilt, so this is what it is. It just has minus z sz cos theta and this form, and then same thing for novel. So so till here is after the pulse we have sx, and then when we take this sx into tilted rotating frame, we have this form. So as we seen earlier, only the z magnetization create I magnetization. So for solid effect case, sz contains the cos theta. I written outside, and for novel case, sz contain free factor as a sin theta. I written here. So this is what we have the density operator in interaction tilted rotating frame. Then once we have the density operator here, so we can just simply substitute the effective Hamiltonian, which time independent effective Hamiltonian, which we got here, this one, and then finally we can simply calculate the density operator at time t. So as I shown earlier, so it commute when it concerned to the double quantum, so zero quantum operator remains same, only the double quantum oscillates as a cos and sine. And same with the zero quantum subspace, so double quantum remains same, and only the zero quantum oscillates with the cos and sine. So this is what we have. So we can substitute back the IZ for double quantum and zero quantum. And for the I spins concerned along longitudinal, this is what we are having. And for S spin, this is what we are having. So when we take the expectation value for I spin, so we get this expression, just a trace of density operator with IZ. This is what we get. For a S spin, we got this one. And when same thing with the zero quantum case, we are getting this. So simply I can tabulate the same thing for the solid effect case and novel case. So for example, a solid effect case for I spin concern, when double quantum is there, so it has this form. So there is a free factor, we call it as an alignment factor, and there is a scaling to the dipolar coupling, that is sin theta. So sin theta for the sin theta is there in the scaling the dipolar coupling, and as a free factor, where in case of solid effect we have cos, and in case of novel we have the sine. So if you see here, the scaling factors gives like how fast we can transfer the polarization. And the alignment factor gives how efficiently we can transfer the polarization. If you see the scaling factor and alignment factor, for novel, it's same, the sine theta and sine theta. So that means that the efficiency is proportional to the Larner frequency and inversely proportional to the offset. Proportional to the nutation frequency of electron and inversely proportional to the offset. And in case of solid effect, the scaling factor is proportional to the nutation frequency and inversely proportional to offset, but the alignment factor is proportional to the offset. So to get very efficient signal, we have to be in a balance between the offset and nutation frequency. Same thing we can see for the modulated case, like top DNP XIX and TPPM case, where we use tilted modulating frame. So so I will show how we do that. So unlike earlier, now the microwave irradiation part contains the time dependence because of the modulation. So once we have, as I mentioned before, we have to tilt so that the effective rotation is happening along quantization axis. So for that, we find theta and phi using the quaternions, and then we tilt so that the effective rotation is happening along quantization axis. Once we tilt it, then we transfer it to the interaction frame to find the effective coupling Hamiltonian. So this is what the interaction frame is defined here. So when we transfer our spin system, the interaction frame defined with the propagator U0I and U1S. So this is what this is concerned to the I spin. So you get this time dependence, and this transformation concerned to S spin. So in this transformation, S can be written as time dependent part as given in this expression. But finding these Fourier coefficients is not straightforward because this is time dependent expression, so we cannot deduce the Fourier coefficient analytically. So what we have to do is we need to find the trajectory, and then we have to Fourier transform to find the Fourier coefficients. So this is the trajectory it look like in the modulating frame. So it's actually like when you keep applying the pulse block, so the magnetization, the S spin, SZ spin going from in the trajectories like back and forth, and also it doing the rotation along the effective. So it has two frequencies. So in it, so they are incommensurate. That is, one is doing the modulation frequency, and it's also doing the effective rotation together. So they don't have common cycles, so we cannot Fourier transform these trajectories. So this is when we tilt it to the z-axis. This is how it looks like. Still it is non-cyclic trajectories, but we want trajectory that has cycles like this. So this is the trajectory. We have both the frequencies, but it contains the modulation frequency and effective frequencies. We cannot separate them from this trajectory. So what we do is a simple trick. So this is the SZ of t in the interaction frame. It's given like this. So these Fourier coefficients we are interested. So we can find these Fourier coefficients simply taking the trace over the corresponding operator. So like this. And once we have the trajectory, and then we can sandwich so that we can take the effective frequency dependence from this trajectory. So here to here is this. Now, if you just look at the blue trajectory, this is having the two frequencies, and when we apply this unitary transformation, the part concerned, it only having the modulation frequency dependence. So then we can simply, once we have the form like this, we can simply apply the remaining U effective to find the final expression. So when we see the trajectory, once after applying the U effectives concerning to the blue part, it looks simply like this. So we have started with the trajectory contains two frequencies, and we deleted the effective frequency contribution, and we left out only the modulation frequency. So this is the crucial part in trajectory analysis. So once we have only the modulation frequency dependence, we can simply Fourier transform to get the different frequencies and the corresponding Fourier coefficients. Here it is the frequency of 3 modulation and higher harmonics, and they have the different Fourier coefficients. So we can substitute these Fourier coefficients corresponding to different frequencies in the SZ of t, like it has an infinite number of Fourier frequencies and their corresponding Fourier coefficients, and then finally we can calculate the effective Hamiltonian. So once we have the effective Hamiltonian at the matching condition, that is corresponding to the time independent part for the double, this is the double quantum and this is the zero quantum. When we match all these time independent parts to 0, so this is what you get. And for when we match all these time dependent parts so that it gives time independent Hamiltonian terms. And then we can simply calculate the final density operator at time t, like we did in earlier case. So once we have calculate the tilted rotating frame Hamiltonian as given here, then we can finally give the double quantum and zero quantum density operator at time t with these simple expressions. Then we can simply find the corresponding IZ contribution from this expression, and then for the double quantum concern, and this is for the zero quantum. And then finally, we can calculate the contact curves corresponding to the different scaling factors. So this is for top DNP. This is the trajectory we see for top DNP, and this is for XIX. So these are the corresponding scaling factors calculated from trajectory analysis. Once we calculate the scaling factor, we can substitute in the analytical contact curves, and we can also compare with the numerical simulation. This is a comparison between analytical contact curves we got through trajectory analysis and with the numerical simulations. So we see that there is a 1-to-1 match with the numerical simulations. So this is what the scaling factors we calculated using trajectory analysis, and it clearly shows that the TPPM here has a higher scaling factors, and that reflects in the shorter bulk buildup and higher enhancement. We can say that faster electron proton transfer is associated with the larger scaling factors, and they cause for the shorter buildup time along with the higher sensitivity. And coming to the summary, description we used here is for the polarization transfer is quite similar what we see in recoupling and decoupling experiments in NMR. Faster electron proton transfer is associated with shorter buildup of bulk nuclear polarization and also higher sensitivity. And experiments at 1.2 Tesla shows that TPPM DNP gives highest sensitivity. And TPPM XX and top DNP figures are suitable to do the mass DNP. And also the characterization of this electron and proton polarization transfer alone does not explain all the experimental observations, because we need to take more realistic system to do the numerical simulations. And here is an acknowledgement, and I would like to thank Jennifer Mathis for giving me the opportunity, and I would like to thank my colleagues Charlotte Weiss and Sanjay Vinod Kumar and Shiva Anandi, and also I would like to thank Age Drescher and Mikhail Ajar for technical support. And I would like to thank Workshop Uni Konstanz and particularly Bruno Arne for helping us in building the tuning works, and our funding agencies Amin Neuter and Hyperon SFB 1527. And I would like also thank Department of Chemistry for all other facilities at University of Konstanz. Thank you. Yeah, thanks for your patience and attention.